Okay, so.
Go. Yep. All right. So welcome back, everyone. I appreciate your pain tolerance. Let's sort of start talking a little bit about how you can construct these K-alpha coherent matrices. So it bears some discussion. Okay, so and there are some nice connections here to error correcting codes. So in particular, that's the answer. There are a whole bunch of error correcting codes, so ECC. That give these things. And effectively, most of the algebra and sort of number theory that I said could be involved with this comes from this connection. So here is sort of definition of the types of codes that are going to correspond most easily with these types of matrices. So we want codes over the alphabet 0, 1, right? We want to have codes whose entries are 0 and 1. So I'll say a code. And I'm just going to consider that restrictive type of code over that alphabet. All right, these are effectively going to be the columns of our matrix. And these guys are going to be a subset of 0, 1, m. Right, there are n of them. So this code is going to have two parameters that are very common in the error correcting code literature. So it has Hamming weight in the setting where they're over the alphabet 0, 1. And I'm going to call it K for reasons that will become obvious now. And this is going to be equal to the minimum number of non-zeros in an ECJ. Right. Okay, so in other words, a number of ones. That's what the Hamming weight's going to be. And the minimum Hamming distance, which is another thing that you'll find if you remind yourself or look up what an error correcting code is for the first time, is defined in that literature to be the following. So I'll call it delta. It's going to be the minimum for two different code words, so J not equal to L, of the number of positions where they disagree. And since these are codes over 0 and 1, that's just going to be the difference of these two guys in L1 norm, if you want to write it that way. So that's the number of places where these guys disagree. That's the Hamming distance. Bigger Hamming distance is a better code. Okay, so this is the minimum number of entries where any two code words disagree. So there are tons of error correcting code constructions over this alphabet and a bunch of other alphabets, and you can there are sort of standard ways of turning error correcting codes over bigger alphabets into codes over this alphabet. So many ways of doing this. So here's a simple lemma that gives a relationship between any of those things. You can Google online. So and these K-alpha coherent matrices we're talking about here. So any code like this right, that we have been talking about. I guess I'll start indexing things at 0 again. With Hamming weight K and Hamming distance delta. So H weight is going to be Hamming weight. And Hamming distance delta is going to be a K minus delta divided by 2 coherent matrix. Okay, so if you get one of these guys and you manage to make K large and delta small, then you have sort of a big K and delta large and K large and delta large, right? Then you have a good K alpha coherent matrix where K is large and this is maybe small, right? So here's a sort of proof of this lemma. Just for the sake of saying that I have a proof here. So first thing, the fact that, so Hamming weight corresponds obviously to the number of ones, so there's nothing to prove there with Hamming weight and the number of ones being K working. All right, so remember, the Hamming weight is a number of non-zeros, so that's a number of ones. There are only 2 things in the alphabet, right? So that part is not bad. So let's look at the inner product of any 2 of these code words. So I claim that the inner product of any 2 of these guys that aren't the same is going to be equal to the distance K minus the distance of these 2 code words divided by 2. And let's sort of see why this is true. So let's start by sort of representing this first vector as let's suppose without loss of generality that all of its ones are in the beginning and then we have a bunch of zeros afterwards. So I'll just put all of the ones of this first one in the first few spots. Doesn't really matter. So the point is that this CL, so this is my CJ. If I look at what my CL looks like over here and sort of notice this following pattern, for each of these entries, every time I have a 1 that has been changed to a 0 over here, so that increases my Hamming distance by 1, I have to have a 1 sort of pop up here. So this is going to flip this 1 to a 0, and one of these zeros has to flip to a 1. So I made a Hamming distance change here of 1. If you look at this guy, but the inner product's going to decrease by, or sorry, I made a Hamming distance change of 2, so a 0 became a 1 and the 1 became a 0. But the inner product's going to decrease by 1 only between these 2 guys. All right, so this will be 0 anyways, and this thing I'll just lose 1. So that's sort of why this equality holds. And then, so then I use my uniform bound, which is the definition of delta here, to bound that inner product. And I get that this is less than K minus delta over 2. And that is effectively the proof. So in fact, without saying so explicitly anywhere that I recall anyways, those of you who are familiar with the compressive sensing literature, Ron DeVore had a deterministic and explicit construction of an RIP matrix. It was the first one, I think, back in like 2007 or something like that. So DeVore's RIP matrix construction was a Reed-Solomon code in disguise. If you look up what a Reed-Solomon code is and you go back and read Devore's proof, you'll see he wrote down a Reed-Solomon code. Right. So in fact, the only explicit constructions that are the most popular ones that are known anyways are actually of this type. They're basically error correcting code constructions. Okay. And the sort of second thing to point out, so the same phenomena that led to Devore's construction and other coherence-based constructions having a number of rows that scales quadratically into sparsity. If you know about this stuff, it's good. If you don't, it doesn't matter. But that same sort of phenomena means that in general, any approach of this kind using error correcting codes is going to end up scaling quadratically in sparsity if you want the accuracy theorem to hold. So that's sort of the problem that we end up having. So we have deterministic, in fact, many deterministic constructions for our matrices. But we also have order S squared rows times additional log factors that I'll ignore. I'll put a tilde there to say I'm ignoring log factors. Rows are going to be needed. But if you do that, you have a completely deterministic method that will get you the guarantees that we were discussing before. Final thing, if you want to improve for a particular X and get a randomized construction that still works, I just want to point out that order S rows are possible in a scheme that uses the same median recovery method and the types of stuff I'll talk about later. If you are okay with a for each sort of probability of failure for each individual X, which you can drive to be as small as you want, but still, if a randomized guarantee of the same quality that we had holding deterministically before is okay, happening with high probability. So I'll just sort of summarize that way. And if you want to see, how that works, you can look at a paper called Compressed Sensing with sparse binary matrices. It's a paper of mine, sparse binary matrices. Blah, blah, blah. It's a paper of mine from 2014 and in the Journal of Complexity. Okay.
Mark, just a question. Do you mean order S up to log factors?
Yes, up to log factors. So I'll spare you trying to write down what the log factors are. They're reasonable, but they are definitely there.
Great, thank you.
Okay, so just wanted to point out this nice error correcting code connection between these types of matrices, and also that this K alpha coherence incoherent matrices are also incoherent, right? Which is all that you need for Devore's types of arguments to work. So you have this sort of connection to those prior results as well built in here. Okay, good. So maybe back over to the other side of the board. Let's start talking a little bit about finding these heavy elements. So the set that we defined last time. So these are the heavy entries of X. So the entries of X that are bigger than the to remind you what it looked like. The best S term, approximation error divided by S plus the infinity norm of n. And I believe we multiplied all of that by beta. Now, beta is ultimately going to end up being fixed to be 2 pretty soon so that we don't have to worry about it because it's kind of just gives you more flexibility that isn't going to help us going forward. So these guys are the heavy elements, just to sort of remind you what they are. Okay. So I brought up error correcting code, so we're going to use similar types of ideas. So what happens in these methods in general is the following. So we are going to learn or find, I guess is probably a more accurate way of saying it, encoded versions of each element in this set. So in this heavy set of elements. Okay, in fact, we're not going to be able to do that perfectly. So what we're really going to do is learn a small superset that we then have to show is not too much bigger than this guy of this set. And that's what we'll be able to guarantee. Okay, so how are these elements going to be encoded? Well, each one of these guys is going to be encoded as an element of an error correcting code. Okay, that's ultimately what we're going to do. I'm not going to try to kill you by talking about it in generality. So I'm going to try to give you a couple specific examples of what that looks like. And then we can go into the Fourier friendly one, and that'll transition us to the sparse Fourier transform techniques that we really care about. So, all right. So let's work with K alpha coherent matrices. They seem a little bit easier. So let's encode it as a column of a K alpha coherent matrix and just understand that there are relationships that we can force to happen where these have something to do with error correcting codes. So, so we're going to encode each entry of this, each n, where this holds, as an element of a really small K alpha coherent matrix. So first of all, see why this is going to work. We can notice the following simple fact. So a K alpha coherent matrix M of any value where alpha is less than K, so where the inner product is less than the total number of ones, right, can't have repeated columns. Okay. Sort of clear. If you did, then the inner product would be K and it would then violate the alpha constraint. And what does that mean? What does that mean for us here? That means that if I consider the function that simply takes elements of my column index set, so column numbers, and maps them to the column of M that corresponds, right? So this is taking a column number and it just spits out the column of M, right? So this is maps N to the nth column of M, right? Really simple. Any matrix you write down is this function being written out on the chalkboard. This is always going to exist clearly. And remember, I had said something about us wanting to be able to identify these MN matrices quickly that we're going to use for in our median recovery algorithm. All right. So we want to be able to identify where the ones are in the nth column of this thing really fast. That's going to be associated to this, right? This is sort of, if we can do this really quickly in like order M time, we'll be able to tell where the ones are pretty fast. So that's directly associated with this thing. And it turns out to find the heavy elements, we're basically going to want to invert this function. So we're going to end up learning what the column of one of these matrices are. And I'll describe how you can do that with an example in a second. And then once we've managed to figure out what the column of this matrix is, we want to somehow invert that and get the n back. So tell us which column of our matrix is this. And we want to be able to do that really fast, right? Without having to look through the entire matrix, which is too large for it to be interesting, right? We need a sublinear-time algorithm. Reading all the columns, even reading through the column in one row is too long. So we can't do that. So crucially, we want F inverse here associated with M to be quickly evaluated, or evaluatable, I should say. Okay. Good. All right. So I'm just going to write down now an example of a particular matrix and show you how this works. It's sort of the most commonly used matrix for this purpose in this combinatorial compressive sensing literature. This is still the theoretical computer science stuff that we're talking about here. So, all right, so let me write down an example of a matrix that has this nice property that if I have a row, I can tell you immediately what column it is quite quickly. And also I can generate the columns really quickly for any n. So I'm going to have a forward and inverse map for this matrix that's really easy to do. Okay, so here's the example. And if you look in that heavy hitter streaming sort of literature, you can find this often called a bit testing matrix. Although I should also point out that this is effectively a parity check matrix for Hamming codes. So it has an obvious error correcting code analogy again. All right. So this is how we're going to do this. So here's how I'm going to construct this guy. So for any number of columns I want to be in, I'm interested in this and in generating my matrix, my bit testing matrix sub n. Okay, it's going to be a 0, 1 matrix as we require it to be. It is going to have 1 plus the ceiling of log base 2n rows always, and n columns, right? And it's really easy to generate the forward map of what the jth column is for the following reason. So its jth column is equal to j in binary. Done, right? I can generate that quickly. You want to know what the jth entry is? I write out j in binary, right? So that part is pretty easy. So here's an example. So B8, right? I am going to, so one other thing, it's the jth column, it's j in binary. I'm going to put for rows, for reasons that will become clearer soon, I'm also going to add an extra row of ones at the top. So it'll have one, that's why it has one additional row, right? So plus a row of ones at the top. Okay, there we go. All right, so I'll stick those in. So this is going to have 8 ones at the top, and then I'm just going to write out 0 through 7. So I'm indexing everything from 0 to n-1. This is one of the reasons why that's a little bit more convenient, right? So my I'll have 0 in binary, 1 in binary, 2 in binary, 3 in binary, right, etc. 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1. Right, boom. You can do that pretty easily column by column on the fly. So 0th row is all ones. Here's my 0th column. As an example. Okay. And not only can I generate the entries really quickly, but I can also, given any column of this thing, I can tell you which row it is also using this structure, which is pretty fast. Right. So if you give me the jth row of this thing, I can tell you what it is by just summing up the bits. Right. So what is it? I'm going to start with the first column and read off the bit sequence and add it up and tell you what the bits are. So this is clearly going to be a pretty fast inversion algorithm here, right? It's like log n time. So 0th entry, I sum up, I get 0. First entry here, I get, right, 1 plus a bunch of zeros, etc. Right? So mapping columns to rows of this matrix is super easy. Okay. So easiest example. So what does this mean in terms of solving linear systems? So why is this at all a useful thing? So this means that Bn times x equal to y, right? So I have this linear system I want to solve. So this can be solved in order log n time for all one sparse x. That's effectively all I'm saying here. So why is that? Why? Because if this is one sparse, it's just going to be a canonical basis vector, and it's going to pick out a column of Bn. And so y is going to be some multiple of a row of Bn. Right? So that means that what I'm going to have here is that x is going to be equal to whatever the let me see. So the non-zero entry, let's say the non-zero entry has size gamma, right? So we can find the we're going to get a multiple of this 0, 1 matrix. All of the entries are going to have the same value if it's one sparse, so it'll be gamma, let's say. And so x is going to be given to you by gamma times f inverse of Bn B sub n times 1 over gamma y, where we know what gamma is. So gamma is the first non-zero entry you find in y, is any non-zero entry. Right, so for a really restrictive, ridiculously simple sparse class of matrices, you can very rapidly solve this system, and that's sort of what we need. So building off of this, you can now see that you can approximately solve almost one sparse systems like this really efficiently as well. So, and doing it will give you what's known as the sort of bit testing algorithm for finding support of sparse vectors. So finding the heavy elements that we want to find. So let's see how to do that. I will go back over here. Well, are there any questions about this before I cover it up? Maybe I should ask that. Yes.
So by just I guess to get some knowledge, right? Like so for one sparse, is that like literally there is one non-zero entry, or that's the
Yep,
best?
there's one non-zero entry, you don't know where it is. So it's one of n choices.
Could be 0 too, right? Could be the zero vector too. right?
It could be the zero vector,
At
yep.
most one non-zero.
That you would know because there would be no non-zeros, so you could solve that also. But yeah, exactly, 0 or 1 sparse. And so your only job is to find where the non-zero entry is, which is basically what this is telling you. It says, hey, there's one non-zero entry at whatever this value is, and its size is whatever the first non-zero entry was in Y. And so this tells you what the answer to this simple problem is. Right? So there is a relationship between this error correcting code mumbo jumbo and solving very simple linear systems of a prescribed structure is all I'm really trying to say. That make sense? Okay, good. Okay, so now I will cover it up and continue on over here. So you should probably be thinking now, like, maybe that's kind of cutesy, but it's obviously useless because that's never going to happen, and that's correct. So you need something a little bit more tolerant to not exactly one sparse objects. And that is what we'll talk about next for these guys. Okay, so instead, suppose we have a slightly, and this also looks simple, but this is just complicated enough that we can actually ensure that this happens a lot using K-alpha coherent matrices. So this is actually just general enough that we can force it to happen. So instead, suppose that for some reason, your signal or maybe some modified version of your vector looks like a canonical basis vector where you don't know J times some number, right? So this is what we had before, but now we allow an arbitrary other junk to be added on there as well. And we just have to say that, so J is unknown. And gamma is large because this is maybe an important entry in a sub portion of our original X. This was going to end up happening. It's large compared to this just bigger than the one norm of this N, this noise vector that you've added on here. So in other words, we're saying, what if X is approximately one sparse? Right? So you can still approximately solve this system using the same type of approach. And the way you're going to solve it is just identifying J and getting an estimate for gamma, right? So that's sort of what happens inside of a lot of these sublinear time algorithms. So, and it works. So identifying J, which is finding the support, is by far the most important thing to do here. So that's going to be what we really want to do right now. So, and it is entirely done by using the following trick. So notice if the elf bit of J, whatever it happens to be, we don't know it, is 1, okay, then Bn of X, if I look at the elf entry, so that's the bit I'm currently trying to reason about. So this is going to be equal to, so let me go back and sort of show you how this example looks. You'll see what this is equal to. When I make this claim, it should make sense. So if I look at the elf bit in my example here, sorry, I'm going to be looking at an inner product of the elf row of this guy with X, right? And what is this? It's actually going to be summing all of the entries of X whose elf bit is equal to 1, right? So the column, each column is is the column number written in binary, but similarly, this row sums all of the odd columns, right? This one sums all of the columns that whose second bit instead of the first one is 1. So these are all the things mod 4 that have particular remainders. So 0, 1, 2, 3, right? So it's 2 and 3 mod 4, right? And that's the pattern I'm getting with these guys. So if I take an inner product of this with X, I'm going to be summing everything whose alpha bit is, or mod 2 to the L minus 1 is equal to 1. So same difference. So that's what we're getting here. So if you think about it for a little while, this is going to be equal to xk, the sum of all the entries of X, where K as its alpha bit equal to 1. Right, so those are the entries of X that I'm going to sum up here by construction of this BM matrix. Okay. So if J's alpha bit is equal to 1, then J is going to be in there. It's going to be in this sum. So this is going to be equal to gamma, which is something quite large, plus some other stuff. So plus K not equal to J with alpha bit equal to 1. Right? And this entry should be quite big then, because gamma is quite large compared to all of these other entries of X that we're adding up. Right? So this should be big. And what should be smaller are the sum of all of the rows where the alpha bit is equal to 0, and we've also encoded those. So that's why I included this row of 1. So remember, this sums up all of X. So it was a row of 1s at the top. We put a row of 1s at the top, and then I'm going to subtract off the Lth entry of this guy, right? And this is going to be equal to the sum of all the xk where k has alpha bit equal to 0. Okay. Yes. And so I should also point out that well, yeah, that's fine. So in this case, this is just nk. And in this case, I can actually remove the condition that it's k not equal to j and write this as nk as well. Right. So I've picked out j and I have whatever the jth entry of n is plus all the other entries of n. And so now you can see, right, if gamma is really huge compared to the 1 norm of n, then clearly this guy is going to be bigger than this guy. Okay. So what do we have? At the end of the day, from thinking about things this way, well, we have a little test, which is why this matrix is called a bit testing matrix. Right, so therefore, if the Lth bit of j is equal to 1, then it implies that this comparison that I made is going to hold. So in fact, the absolute value of this guy is going to be bigger than the absolute value of the odd sum of these noise entries in that case. And in fact, you can reason the same way about the Lth bit of j being equal to 0, implying the opposite order, and then using the fact that there are only 2 possibilities, it's either 0 or 1, to see that in fact this is an if and only if by symmetry. Right, so that tells you effectively that you can solve all of these approximately one sparse problems by doing this simple bit testing stuff, right? And so what do you need in order for this to work? You have to isolate one heavy entry of this type from our CS beta set with arbitrary noise whose one norm isn't too large. And then you win. Okay. Good. All right. So, all right. So let's layer this up a little bit and see how to make this fairly simple method work for us. So, and this will also tell us what types of measurements we really are going to use for our set identification portion of the algorithm. How much time do I have left?
You start, I think 20 minutes.
20 minutes? Okay, good. I was like, ends at 4, dang.
Yeah. 20 minutes, yeah.
Okay, 13 minutes or something? Or?
No, it's visible will be 4:15, but you start a bit late, so yeah.
Okay, yep. All right, so let's keep this sort of trick in the back of our minds. Remember, it uses this BN matrix and we can do all this stuff. Okay, so now let's talk about the sort of measurements that we can use to identify heavy elements. So this is the real sort of measurements that are used in these sublinear time algorithms. They sort of always end up looking something like this. So, so the measurements that will allow recovery of our heavy elements, CS beta. Okay, so they're going to look something like this, and I apologize in advance. So here, I'm going to use this Catry-Rao product, and I'll define what it means, but you can look it up. This is going to be a row-wise Hadamard product. Of two matrices. So that's just something to Google, and I'll give you an example of what it looks like in a second. This is going to be what we end up using to recover the important entries of something. Okay, so I'm going to take a K-alpha coherent matrix. So this is going to be some error correcting code, and probably I'm going to want K to be 4 alpha S plus 1, right? So that the accuracy theorem holds for our median recovery stuff. And I am going to take this row-wise Hadamard matrix with one of these bit testing matrices as an example. Okay, so if I do that, all pairs of rows of Bn are going to multiply all pairs of rows of M. So the number of total rows is going to be the product of the rows in these guys, in both of these guys. Okay, so this is going to be a 0, 1 matrix because they're all 0, 1 matrices. It's going to have M times log base 2n plus 1 rows. And it's going to have n columns. All right. And more explicitly, its rows are going to be, each one of the rows can be indexed by choose your row of M and then choose your row of your bit testing matrix, and you take a Hadamard product of those guys. So what's that going to look like? All right, so the kth row of M, I'm going to do a Hadamard product with whatever your favorite nth row of Bn is. All right, so this is now a Hadamard product. And what is a Hadamard product? It's just an entry-wise multiplication of the two, right? The entries in the vector. So, so we have this, and this is for all rows K of L of M, sorry, and all rows L of B. So a little bit nasty, but not too bad. It just takes some mental processing. So these are the actual measurements which are going to allow heavy entry identification. And the next thing you should ask is why, and it's for a really easy reason. So let me try to convince you of that. So why do we want these gross measurements? Well, the answer is that because these are all 0, 1 matrices, when I do this component-wise multiplication, I'm just further screening the entries of X that I sum when I hit it with these rows, right? So I'm sort of screening the entries of X that I sum by the elements of my K alpha coherent matrix and knocking out a whole, maybe all but one important one, which gives it the structure we need in order for our recovery from this matrix to work. So that's effectively what's happening. So why these measurements? All right, so what is this hideousness doing? So every one of my measurements is going to look like, right, one of these guys. I guess I should have used proper MATLAB notation here and made it clear it was a row. It was a row and not a, sorry, not a column. So we have this Hadamard product here. So that's what all of our, I mean, everything's real, so it really basically is an inner product. There isn't any inner product of these guys. And the point is, because these are Hadamard products, this is going to be exactly the same as taking this guy, which I can now construct myself, taking inner products with my bit testing matrix, which lets me reconstruct approximately one sparse things. Right, so I can just move this over. It's just entry-wise multiplication, right? So it's just a matter of regrouping what I decide to call what. And then the point is that my K alpha coherent matrix can force this to look like alpha EJ plus N for N in one of our important heavy element sets. Many times, effectively, right? So in the submatrix, for example, maybe I should put it down here. In the submatrix, for example, MJ, it's going to look like this with a bunch of different subsets of N, and then you just argue that a lot of them are going to have exactly the property when this is sufficiently large that the one norms of the noise you can add on is guaranteed to be small enough that you're going to find this guy using bit testing. And that's the entire intuition for how these things work. Of course, proving it all and writing it out takes a lot more time, but that's basically all that's going on. Okay, so I think I now have enough. We've now discussed enough here that I can write down what a support identification method is associated with these bit testing matrices. So let's just write down the algorithm, and then hopefully you'll sort of see intuitively why it works, if nothing else. Okay, so right, so this is going to be support recovery. And there are theorems telling you that you're guaranteed to grab a significant port, you're guaranteed to grab a superset of our important heavy element set. So our input to this guy, we're going to have our K alpha coherent matrix, whose parameters just have to match the accuracy guarantee. That'll be enough from the prior median recovery theorem that we saw before. We're going to put in a bit testing matrix, although it doesn't have to be a bit testing matrix necessarily. It could actually be any matrix that has an efficient inversion column to column number and column number to column sort of algorithm like the bit testing matrix does. And we're going to see another one next time that will show you why this stuff is actually useful for anything involving a function, because I can understand there's probably skepticism at this point. Okay, so we want with a rapidly invertible function FB, right, that takes you from column number to column. I'll call them a B, right? So one of like the bit testing matrix, so we know there is one. And we are going to take measurements which are the product of these two things. This Cattry-Rao, this row-wise Cattry-Rao product of these guys applied to X. So there will be M tilde, let's say, entries of this guy. So I should put that up here. M entries of this guy, so that all works out, right? By a matrix measuring X. Okay, that's good. So that's our input. Our output is going to be a set S that contains I'll show you what we can guarantee, beta equal to 2, let's say. So C beta S, where beta is equal to 2, these heavy elements. And so what do? What does this algorithm look like? We initialize our set that we're going to eventually output with the empty set. That part shouldn't shock anybody too much. Then we're going to go through and do bit testing for our matrix, right? So for A equals 1 to 2M. So we'll go through all combinations of our bigger K alpha coherent matrix. And then more importantly, I guess, for I equals 1 to M tilde, all of our bit testing matrix entries, right? So this is going to be, this inner for loop is going to construct B tilde in C M tilde. In fact, in 0, 1 M tilde, it's going to construct some unknown row of the bit testing matrix that we're then going to try to recover using F inverse. So it's going to be something that encodes one of our heavy elements ultimately. And what do we do next? We do our bit testing trick. So if the inner product of MJ, Hadamard product BI, right, the BIth row of B with X so these are going to be all the entries that have, let's say, the ith bit equal to 1. So that's a sort of bit test that we had before. Are bigger than the alternative, which is the complement set sum of the X entries, which we're always encoding again with MJ X. So we always have a row of ones at the top of our B so that we have all of our original measurements. And now we're going to subtract off these guys, which we also have. So this is MJ. The jth row of M, Hadamard BI again, inner product with X. So that's an X, right? Absolute value. So if your bit is equal to 1, set BI equal to 1. Right? We're doing bit testing for all of our bits. Otherwise, set BI equal to 0. Okay. So now we've filled out all of our entries of our B tilde. So let me call this B tilde I. Consistent. All right, great. We'll end our if I. So 9 is we're going to recover some potentially heavy entry by applying FB inverse to whatever this B tilde is that we just reconstructed with this I for loop, right? We just did bit testing. So this says, hey, I think I uncovered an encoded version of our bit testing matrix that's important. What column is it? N. Right? Yep.
Can you repeat what line 2 says and what the last expression in line 3 is, the Hadamard product?
Oh yeah, so this is just going through all the entries, I equals 1 to M tilde of our bit testing matrix. So all the rows of our bit testing matrix. We have this row-wise Hadamard product. So we're looking at all pairs of rows from M with and from Bn, right? So we're going through all those rows. And this is our bit testing expression. So we're taking the inner product of the jth row of M, Hadamard, the ith row of B, and seeing if it's bigger than the inner product of the jth row of M minus the jth row of M, Hadamard, the ith row of B. So this inner product is the same as this inner product, just crushed. Sort of similar to our prior example. Yes, apologies, my board space issues there.
Mark, there's a reason why we go from 6 to 9 or just.
I can't count.
Okay.
Which should make you suspicious of all the combinatorial results in here, I guess. Yeah, good. Or not. All right. Perfect. So, all right. Yes. And so now what do we do? Yeah. So let's go ahead. We're now going to go ahead and collect this entry in our set, right? We're saving it as something that's potentially large. And I want to sort of emphasize here that you can either save it as a set if you want, or what actually happens in the theorems and is an important point. So I'll sort of mention it. S can be, or generally is, a multi-set. So in other words, we want to actually count the number of times we get each n, because we're going to get some n's many times. Why? Because there are potentially a large number of m's here that we're going through, and for every one of them, we're running this. We're getting one of these guys, and so we could recover several n's multiple times. And in fact, you proved that you do. The important heavy ones recover several times. Okay, so this is end for J. So now I'm done going through all my entries of M. Okay. And then the 12th entry is you proved that effectively at least k/2 of these screened, these versions of M that are screened by the MJs. So at least half of the ones that actually measure each J are going to give you an N whose one norm is small compared to a heavy element, right? So in other words, that means that you're going to recover important things at least k/2 times. Something similar to what I was talking about Simone before. So you output elements of S that you recovered at least k/2 times. Now, by the way, you could just output everything that you recovered. It wouldn't actually hurt you very much, but it would hurt your runtime and make your runtime suboptimal. So I'll just sort of talk about it this way. All right. So this is, I have 3 minutes. No, I'm done.
No, I mean, we would have a Q&A, a free Q&A time for 15 minutes. So I think it's worth, if you feel like you need a few more minutes to close the discussion.
Yeah, so let me just tell you what you can prove about this algorithm, and then I'll let you ask me about all the things that make no sense about it to you, which is probably a few things I would imagine. So what can you prove? So there's an accuracy theorem here as well. Probably more accurate than my spelling of accuracy. Whatever. So when M is 4 alpha S plus 1 alpha coherent, this is the same condition that we have for the other median recovery estimation of coefficients in any set you happen to give somebody. This will produce a set S that contains the set of heavy elements for whatever, for this S, right, with beta equal to 2. So that's guaranteed to always happen as long as M has this incoherence property. And most importantly, if this S were really big, this would be a stupid theorem, right? Because I could just output all of bracket N, and I would clearly have the property. So I need to bound the cardinality of S. So the cardinality of S is also going to be relatively small. So it's going to be less than 2M divided by kappa, or divided by K, I should say, capital K. And this guarantee, this slightly better guarantee than what you might expect, is what you get by bothering to count the entries and the number of times you correct each one. So clearly you're going to recover M elements. M could be on the order of S squared, which wouldn't be great. That would sort of make your set of heavy elements bigger than you might want if you're trying to have a really fast order S time method. So if you pay attention to how often you reconstruct them, then you can guarantee that this is faster on the order of something like, so K is often chosen to be like order S, or M turns out to be like K squared, let's say. And then you divide by K, which is on the order of S, right? And you get something which is order of S big, and then you sort of are happier with life. So, so this thing is actually guaranteed to work under the conditions which I have insufficiently explained. Great. All right, so that's it, I think. Now feel free to ask any questions you may have.
Okay, so maybe we should Peter. Amazing first day of lecture. Yeah, so now the idea was to have an informal Q&A moment. So we have roughly 10 minutes. Could also be, technical questions or big picture questions about these techniques. So also, if people online, if you have a question, feel free to either type in the chat or unmute yourself. I see, Ben, you had a question?
Yeah, sure. Just a technical question. So thanks a lot, Mark. That was a really interesting first day. So just a technical question about this. Are you assuming something about the noise level in in say this final result here on accuracy, do you need your n to be smaller than something?
No, this is, so that sort of consideration is built into what I mean by a heavy set. So if we remember what the definition of this guy was, this sort of included some information about how large the noise was. So
right, yeah, yeah.
So what it's guaranteed to find is some superset of, let me find some free space, right? Well, maybe I'll put it up here. All the entries of X that are bigger than twice, let's say, the best S term approximation error for X divided by S plus the infinity norm of whatever your noise level happens to be. So that's the sort of size of these guys that you're able to find. And so your coefficient estimates are all going to be inaccurate up to an order of the infinity norm of n of your noise. And so in this easy way of handling noise, you end up with, in your total error bound, if you look back at the median recovery stuff, you have like a square root of S times the infinity norm of n sort of appearing there because you have two S entries and they're all off by potentially this much.
Okay, so if my noise is very big, I'm just going to have S being the empty set, basically. If my noise goes up, yeah.
I mean, yep. I was thinking when I was doing this, there are actually error correcting code ways of handling the case where you have a small number of entries that are really corrupted and then more that are more reasonable. You can actually, but I mean, it's not published anywhere. So you can do things like that. But yes, if you have like totally horrible noise added to your measurements, then you would expect you're going to probably have junk, right?
Yeah.
And you do have junk coming back.
Okay, thanks, Mark.
Okay, so other questions in the room or? Yes.
So to go through the algorithm website for the structure, so it's like there's two for loops, right? Like
Yep.
for loops. And in the innermost for loop, we have that if condition based on that like
Yep.
equivalence.
So think about the bit testing example here, exactly. So what this is saying is effectively, so remember that inner product, that little inner product equation that I wrote down where right, we have this guy VI, right? This thing taken with X is equal to this other equivalent thing where I just take my bit testing matrices and apply the inner product to MJI or MJ, the Jth row of M, Hadamard product with X. So the proper way to think about what's happening in here is for each choice of J, I have a screened version of X. I've basically allowed myself to effectively zero out a bunch of entries of X. So I've like decimated it's what I can sum over here. And then I'm bit testing that. So for each J, yeah, and then so the way the theory works is you say, okay, for most entries of J, if the entry I'm currently, one of the heavy entries is in this set that I'm sort of hitting, it's going to lead to a situation where bit testing works. So I'm going to have a heavy entry that dominates the one norm plus noise that's smaller than the one entry that I really want to find because it's a heavy one.
Would you say that like doing this Hadamard product, like the way to, because I'm not very familiar with the operator, would you say that like the best way to intuitively to like think about like what that's doing is just preparing us to like do the bit testing well?
Yeah, yeah. So that's sort of why these are 0-1 matrices to make it more clear that you really are effectively letting yourself through your measurement process artificially zero out portions of X, which you don't know. But you're doing it in a very sort of structured way that effectively separates the important entries from one another. So if there are S important entries, you're guaranteed to end up with some rows where this Hadamard product kills all of them except for one, and then there's some other small stuff floating around that you can deal with by bit testing. Yep.
So if I just put on my continuous optimizer hat and play devil's advocate, why would I go through all this combinatorial pain when I can just use, I don't know, a lasso formulation and run accelerated proximal gradient? And what I mean, of course, you're gonna probably kill me, but like, why would I do that instead of like 2 lines of code?
So computer scientists do this because this method works when n is a trillion.
Oh. Okay, well, okay.
This is
When is
vector in streaming data applications. That's why they're first. So that's why they develop these things. So they have streaming algorithms where you're looking at, let's say, all the data, all the sales that all the Walmarts are sending to their headquarters continuously all the time. And so they have updates, which is why the linear measurements help. So sold 2 bottles of shampoo and a toothbrush, and it's coming into your server. And you want to keep a sketch of this data because you can't save it all. It'll destroy your computer. That allows you to answer questions like, what are the S products that we're selling the most of in the last 2 weeks? And you have to be able to answer them on the fly. So like anytime an executive asks you the question, you need to be able to tell them. And you have to, be able to deal with all of the 100,000 products that they sell. So, and there's like 100,000, but the recovery has to be so fast that you can do this and sort of keep track in real time so if you have an optimizer that's fast enough to do it in real time, you should go tell those guys about it. You could be looking at stock market trades and want to know which of the however many companies exist have the highest trading volume. The reason why these were developed, people were thinking about these things at AT&T Labs because N was a number of phone numbers, and they wanted to know if there were phone numbers out there that had suspicious numbers of calls emanating from them, which was an indication of like fraud in the 90s or whatever, right? So from your viewpoint, think of something, N is a billion, 100 billion, a trillion. So in the context of Fourier approximation, we're going to have functions of many variables. So let's say it's a function of 10 variables, and we want to take a small number of function samples and try to figure out what the 100,000 most important frequencies are in maybe a space of, maybe you want to have 100 frequencies in each of your 10 dimensions. So it's 100 to the 10th power is your N. And your S is 100,000. And again, if you can solve that with the convex optimization method, I would use it. So that's a situation. Think astronomically large N. That's where
Said N is too large.
Well, I mean, there are real examples where N is very large. That's all I'm trying to, and that's what motivates it. But yeah, no, if N is small, you're insane to do this sort of stuff. I take that. I agree with that point. You can still fairly quickly find an answer that with fewer measurements that of similar quality using a convex optimization method. I agree.
Other questions? I had a last quick curiosity on the fly. So the paper you mentioned by yourself. So with the O of S measurements, I guess.
Yes.
So is that still based on the coherence? So how do you break the coherence quadratic bottleneck there? Is it still based on the coherence, or it's a different approach?
There you are interested in estimating 1x. And so these are for all guarantees with S squared, like it's going to work for anything that you throw in there deterministically. So for 1x, you can subsample your low coherence matrix, and depending on how structured it is, you can do it more or less intelligently, and get a much smaller submatrix that'll work for a particular vector x, and that's sort of all that's going on there, just doing it carefully. So, And then with high probability, whatever that fixed support happens to be for whatever you happen to have measured, as long as you subsample your set of rows properly, you'll get something that scales linearly and S times small log factors. That's sort of how that works.
Okay, thank you. So I think,
One thing that might be useful though, in that sort of hybrid approach, is suppose N is a little bit bigger than you want. Some of these tricks might help you figure out where, maybe a better initial place to start.
Yeah.
For example, it might say, maybe you should try these support, N is 5 times bigger than I like. Maybe you can try this subset of sort of solve on this restricted support set and get a good answer, at least to start, and then see what happens. So, the tricks here might be so I'm putting them in here to get these extreme run times and stuff, but some of the tricks might actually still be of value in more, other solution approaches.
okay, so I think, let's thank Mark again for today.
Everyone's clapping. I just clap when other people clap.
Tomorrow at 2 p.m. 2 p.m. East time for the people elsewhere in Canada or US. So yeah, see you tomorrow.